Welcome to More Learn, More Teach, where I attempt to simplify the complex. Hello. Today we're going to talk about water. Okay, so water, H2O, right? So it's made up of oxygen and hydrogen, right? So oxygen 16, it's got 8 protons. So if it was just oxygen by itself, it would have 8 electrons. Those would be in the 2 in the 1s shell, 2 in the 2s shell, and then the remaining 4 would be in the 2p shell. Hydrogen by itself is going to have 1 electron in the 1s shell. So both hydrogen and oxygen want to have full shells, so they will come together and they will covalently bond. Covalently bonding means that they will share electrons. They don't give up electrons, they share. They just stay close enough to where they feel the effects of the electrons very closely, right? So they're so close that this hydrogen 1, which has 1 proton, considers itself to have a full 1s shell because it is sharing one of the 2p electrons from the oxygen 16. The oxygen 16 is sharing this electron from the hydrogen, helping it fill its 2p shell. It's going to do the same thing with the other hydrogen atom, right? So because of that, I now have a oxygen 16 that has a full shell, right? The 2s and the 2p are full. So I have 6 electrons in the 2p shell and 2 electrons in the 2s shell, meaning I've met the octet rule. So I have a full valence shell for the oxygen 16. I have 2 electrons in the 1s shell of the hydrogen 1 on both sides. So I've satisfied that requirement. Okay. Overall, I have 10 protons and I have 10 electrons. So overall, I have a neutral charge. However, due to the geometry of this bonding, I'm going to have a slight positive charge where I have my protons, right? So where my hydrogen atoms are located, I'm going to have a slight positive charge. So I'm going to say slight positive. It's not even a whole electron worth of positive. It's just slight positive. And because I have a overall 0 charge and I have a slight positive on this side, I must have a slight negative on this charge. Makes sense, right? Because I'm going to have more electrons over here anyways, right? I have more electrons on the oxygen side, have these exposed protons, right? These hydrogens. So I'm going to have a slight positive on one side and a slight negative on the other side. The reason that's important is because this is a overall neutral molecule. However, this polar covalent bonding structure gives me the effect of a charged particle. So as this water molecule travels through whatever substance, even itself, it will have charged particle interactions. It will pull and push based on negative charge and positive charge, right? Like charges will repel and unlike charges will attract, right? So it will attract other water molecules. It will also repel other water molecules. It will add to that average random molecular kinetic energy of the substance, okay? So as I mentioned, I will have some average random molecular kinetic energy. That is an indication of the temperature, right? So today we're going to limit our discussions to liquid water. Liquid water defined as it has enough energy to where the water molecules are mobile, but not so much energy that it loses its fixed volume, right? So it's got a fixed volume, but the molecules can move around. Okay, that is a liquid. So since I have liquid water, I have some average random molecular kinetic energy that is going to cause these things to move around. When they collide with each other, sometimes they will hit with such force that it will deprotonate, right? It's a fancy word for saying it's going to rip off one of these hydrogen nuclei, right? So the hydrogen nucleus is going to be ripped off, leaving behind this hydroxide, right? So this situation is this water, okay, had water. It's now lost its proton, left behind its electron. It just ripped off its proton. Boom, it's gone, right? So that left behind this hydroxide. I still have a full outer shell on my oxygen 16. I still have a full outer shell on one of my hydrogens. However, now I have an unbalance in the charges, right? I'm going to have still have 10 electrons. However, now I only have 9 protons, right? 8 plus 1. I have 9 protons, which means I have an overall negative charge. I have more electrons than protons. So I'm going to have a 1 electron charge, right? So a negative 1 E charge, right? So this guy ripped off the proton. Well, the proton doesn't just hang out there. It's going to latch on to the first water molecule it finds, probably, and it's going to covalently bond with that guy. Okay, but now it didn't bring any of its own electrons to the table, right? It's just going to share. It's going to latch on and share to a water molecule that's already satisfied, right? So this oxygen 16 was already satisfied. However, this guy wants to be satisfied too, so he's just going to mooch, right? So this hydrogen 1, this proton, is just going to get close enough to this water to where it's going to covalently bond, and it's going to satisfy its 1s shell with 2 of the 2p electrons from this oxygen 16. Okay, because it does this, it's going to end up with 1 more proton than the number of electrons, which is going to give you a positive charge, right? A 1 whole charge, right? So you're going to have a plus 1 E charge on this hydronium molecule, right? So I have hydronium ion, hydronium molecule, okay? So I've got some hydroxides, I have some hydroniums, I have some water molecules. This all exists in the same substance, right? At 25 degrees Celsius, so at 25 Celsius, what's called the ionic constant of water is really close, so really close to 10 to the minus 14. All right, so 10 to the minus 14. What that means is if I multiply the concentration of hydroxide, that concentration multiplied by the concentration of the hydronium, if I multiply this by this, I will end up with 10 to the minus 14. So that is equal to the concentration of my hydroxide multiplied by the concentration of my hydronium. The ionization constant for water is 10 to the minus 14 at 25 degrees Celsius standard pressure. That's equal to the concentration of the hydroxide multiplied by the concentration of the hydronium. This is in moles per liter. If I take the negative log of this number, I end up with 14. I can also do some math here to say that negative log of the ionization constant, right? Substituting in the concentration of hydroxide multiplied by the concentration of hydronium. Use the properties of logs, right? So the product rule of logs. I can split this log out, so I have negative log of the concentration of hydroxide minus the log of the concentration of hydronium. This is the POH, and this quantity is the pH. So the pH that I can measure will infer the POH if I know the pKW. So that's how we will use this in our examples. If the concentration of hydroxide is equal to the concentration of hydronium, the solution is said to be neutral. So if that's true, then the ionization constant is equal to the concentration of hydronium multiplied by the concentration of hydronium, right? All I did was substitute in the value of the hydroxide for hydronium. That's going to be the concentration of the hydronium squared. So if that's this squared, in order to find the concentration of hydronium, I would take the square root of the ionization constant. So the square root of ionization constant is equal to the concentration of the hydronium in a neutral solution. If that's true, then the concentration of the hydronium is equal to 10 to the minus 14. Take the half root of 10 to the minus 14. That gives you, using the product rule, 10 to the minus 14 divided by 2, or 10 to the minus 7. So to find the pH, I take the negative log of the concentration. That will give me 7. So a pH of 7 in about the range of 25 degrees Celsius at standard pressure will give me a neutral solution. So for every autoionization of water, I will require 2 water molecules to create 1 hydroxide and 1 hydronium. This will happen such that I have a constant. So if I multiply the concentration of the hydroxide, concentration of the hydronium, this must be a constant. Okay, so if I were to add a substance, such as a basic substance, sodium hydroxide, something of that nature, I will add to the concentration of hydroxides. If I add to the concentration of hydroxides, in order for this ionization constant to remain constant, it must reduce the concentration of hydroniums. And since the pH is equal to negative log of the hydroniums, if this quantity goes down, then the log of that quantity will also go down. It becomes a more negative number. A bigger negative number multiplied by -1 gives me a higher pH. So the pH goes up when I add more hydroxides to the water. All right, so let's do an example. So I have in the stomach, I have a Pareto cell. So a Pareto cell secretes 160 millimoles per liter of hydrochloric acid, and we want to find out what the pH is of that secretion. So if I assume that I have 100% dissociation, it's a strong acid, then all of my hydrochloric acid is going to dissociate. So I have to have water to make this work, right? Because it's in an aqueous solution. So I have hydrochloric acid plus water is going to yield our hydronium plus our chlorine ions. Okay? I was given that I had 160 millimoles per liter of hydrochloric acid. I have, because in order for this to balance, for every hydrochloric acid molecule that dissociates, I must have exactly 1 water molecule. Therefore, if I have 160 millimoles per liter of hydrochloric acid, then I must be using 160 millimoles per liter of water. Again, I have a 1-to-1 ratio. So for every hydrochloric acid molecule that is used, I will have 1 hydronium made. I'll also have one chlorine ion floating around as well. So the pH, so since this is true, the concentration of the hydrochloric acid is exactly equal to the concentration of the hydronium that is added. Okay, so I add 160 millimoles per liter to 10 to the minus 7 moles per liter. 10 to the minus 7 moles per liter is incredibly small compared to 160 millimoles per liter, so therefore it's effectively non-existent. So if I take a pH is equal to negative log of the concentration of hydronium, negative log of 160 times 10 to the minus 3. That's going to give me 0.79588. I had two significant figures, so I want to report my answer in two significant figures. So the pH of the secretion is 0.80. So it's incredibly acidic, which is important because it wants to help you digest your food. Thank you for watching my video. Please like and subscribe. If you have any questions that I can help you out with, I'd be happy to try and answer your questions. Send me an email at morelearnmoreteach@gmail.com.